And the reason why this is kind of an overriding lesson compared to yesterday is that we're talking here about analyzing rational functions in any form. So they don't have to be variations of 1 over x or variations of 1 over x squared. They can be any rational function as long as you have a polynomial over a polynomial and there's x somewhere in the denominator. What we're learning today is how to handle those. It turns out that when you have a non-permissible value for the variable x, and you have non-permissible values for rational functions because they have a denominator that has x, and certain values of x make that denominator 0, and you're not allowed to divide by 0. Okay, it's not that you're not allowed to. Division by 0 is not defined. Okay? You can try it, but it won't work. It turns out that when you find a non-permissible value for a rational expression for x, that non-permissible value manifests itself visually on the graph in one of two ways. It might look like one thing, or it might look like something else. And one of those things is a vertical asymptote, and one of them is what I prefer to call a point of discontinuity, but what the diploma exam very often calls is a hole. And I think, a hole is a good word for what it is, because it is a hole, but it seems like a non-sophisticated way of describing it. It's a point of discontinuity. And then we're also going to talk about horizontal asymptotes, which are removed from what I'm talking about with non-permissible values. Horizontal asymptotes are a different kind of beast. So to begin with, I'm giving you two functions, and we're going to sketch them on a graphing calculator and learn about the different types of non-permissible values for x. So for each of these rational functions, we're going to state the non-permissible value. We're going to sketch them with a graphing calculator. We're going to investigate what's going on the graph when you're close to the non-permissible value. And then we're going to simplify the functions. And the word simplify is a little iffy here. We'll get to that in a bit. But we're going to simplify the rational functions and come to a conclusion about what the simplified form tells us about whether the non-permissible value is this thing or this thing. Okay? Whether it's a vertical asymptote or whether it's a hole. So to begin with, I think it's pretty obvious that in both of these rational functions, the non-permissible value is 2. Right? What we would say is that for each of them, x minus 2 is not allowed to be 0, which means that x is not allowed to be 2. And when I say x is not allowed to be 2, I guess I'm telling you the domain, but I'm telling you that the non-permissible value is 2. Because it's not allowed to be 2, that's what the non-permissible value is. So we're going to sketch these. So we go to the first one. We'll do f of x first. When you enter a rational function in your calculator, you need a set of brackets around the numerator and the denominator unless they're monomials. And even if the denominator is a monomial, you should probably have brackets around it because it might be a monomial like 3x squared. And you don't want to just go divided by 3 times x squared. So it's x squared minus 3x minus 10 divided by x minus 2. And I've chosen functions here that zoom standard is where we want to begin. We might adjust that, particularly for the next one. But these two grids I've given you are meant to mimic a zoom standard setting view on your window. So double check it, looks okay, and I go zoom standard, which is zoom 6. And I get a hyperbola. It has 2 branches to it. It's a little bit twisted. It's not like something up here in the top left and something down here in the bottom right. It's kind of rotated, and that's what I was getting at earlier when I told you that rational functions don't have to look as simple as 1 over x squared or 1 over x. Okay? They can look different. And before we sketch this, I want to just use the trace function with you for a minute and go trace 1. And if you go trace 1, it's calculating the y coordinate as being 12. And I can't see that point because 12 is quite far up on my view. I'm only going up to 10. But if I were to go trace 3, I get a value. I think that's negative 10. So at 1, the function is defined. At 3, the function is defined. If I go trace 2, I just get a nothing response from the calculator. I don't get a y equals. And that's demonstrating to you that y is never equal to some value because x is 2. And why is that? Because x can't be 2. There is no x equals 2 here. So there's no y coordinate that goes with that. But let's go back to trace 1. If I go trace 1 and I get 12, okay, that's fine. What about trace 1.2? Well, I get a larger number for y. If I go trace 1.5, I get an even larger number. If I were to go trace 1.9, I get an even larger number. Now, I'm going to warn you, I'm going to try trace 1.99, and it might very well be that the calculator ends up rounding it to some very big number in scientific notation. Okay? But if I put 1.99 in there, well, I'm getting 1200.99. If I put trace 1.9999, let's see what happens. So I'm getting 120,001, and maybe there's decimals attached there, but my calculator is not showing them. My point is, as I'm approaching that non-permissible value of 2, as I'm getting closer and closer to x equals 2, and I can't get to x equals 2 because then there's no y coordinate, but as I get closer to it, y is exploding. Okay? And let's just keep going with this, just a couple more. 1.99999. I don't know how many more 9s it is, but I'm getting now an incredibly large number. And if I were to do the same thing on the right of 2, I could go trace 2.5, and I get a negative number. If I go trace 2.1, I get a bigger negative number. If I go trace 2.000001, which is not 2, I'm allowed to be there. I'm to the right of 2, but I'm really close to it. What happens is the number explodes in the opposite direction. And this is the kind of the textbook definition of a vertical asymptote, that as you get closer to the asymptote, the graph approaches positive or negative infinity. So let's sketch this. Let's start putting this together. There will be an asymptote, a vertical asymptote at 2. And your sketch doesn't have to be perfect. You're never going to be asked to sketch this on a written response. We're just learning about these things now. It's at 2, and since this is scaled from negative 10 to 10, that would be approximately where 2 is by my count. And if I try to, mimic what I'm seeing here, the graph, I'm going to clear that and do it again. The graph kind of starts about here where my finger is. It goes up. It crosses at 2. It doesn't have to be perfect. I'm not worried about x-intercepts here. And it kind of clips the top of the y-axis a bit. So there's a branch of it that looks something like this. And I've mentioned this before, that I prefer putting arrows on the ends of these things. And the diploma exam would always in the past do that. And all of a sudden now, maybe they just have a different graphic artist. They don't put arrows, and you're expected to know that these things continue. And then we also have this kind of, roughly, I'll go about here. It does not have to be perfect. In fact, if I wanted to, I could make it a little better to make it more symmetrical on both sides of that asymptote. That is not the point. The point is this non-permissible value results in a vertical asymptote at x equals 2. And the other thing we were asked, if you go back and you look, we've sketched the function. We've stated the non-permissible value. We've yet to get to the point where we can compare, but we're asked to describe the behavior of y near the non-permissible value. So what we can put here for this one is, as x approaches 2, the function approaches plus or minus infinity. And we don't need to worry about from the left or the right. I talked about that yesterday. I talked about, well, from the left is either positive or negative, and in this case, from the left it would be positive infinity, and from the right it would be negative infinity. Okay, that's beyond the scope of this course. That's a calculus kind of concept. Now let's sketch this other one. And initially when you see the second function, the graph is going to be a little surprising. Not what you would expect for a rational function. I don't know why I deleted that. I just had to change one number, but that's okay. X squared minus 3x plus 2 over x minus 2. Just double check. Yep. Graph. And the surprising result is it's a line. Okay, well, I'm going to tell you something. It's not a line. This is not a line. And I'm not telling you that it has a gentle curve to it. This graph is straight, and it continues for both directions, in both directions, indefinitely. But a line contains every single point. And x is not allowed to be 2. So just like the previous one, if we go trace 2, the calculator doesn't return a result. There is no y coordinate at 2, at x equals 2, because x can't equal 2. But what if we go trace 1.99? We get a y coordinate that is not getting closer to infinity. It's not getting bigger and bigger. We get 0.99. If I go trace 1.999, this number that was 0.99 is now 0.999. The y coordinate is squeezing in on a value of 1. As I get closer and closer to x equals 2. Now at some point, I'll warn you what the calculator might do is here just round it to 1. Okay? And I don't want to put too many 9s because I don't want to have to explain that when it does show you 1, it's not really 1, it's just a number really close to 1. And it's rounding it. I go on the other side of x equals 2, and I look at, well, what if x is 2.0001, which is not 2. I mean, I'll remind you, we can't use 2. But what if we use a number very close to 2? I'll push it. See, it's giving us 1. It's not 1. It's not. I can... I hope demonstrate that to you by going to my table. It says 1 up there, right? But I think if I scroll over it, it's rounding it. It's not 1, okay? If I cared enough, I would open up an Excel spreadsheet and type this function in, and we could look at as many decimals as we want, and it would not be 1. It would be 1.00000 something. Okay? So there's a totally different behavior here, which means, everybody, that there is a hole in this graph. This is the bizarre thing to think about. There's a hole in this graph that's infinitely small. There's an opening in it, but it's infinitely small. You can see the hole many times if you change the zoom setting to zoom decimal. And we don't need to worry about y, but if you go zoom decimal, which is zoom 4, you can see there's an opening there. There's a little hole. And it's not really accurate of what we're talking about because the size of that opening is so small you shouldn't be able to see it. But your calculator, because it's using a different window setting or zoom setting, is showing it to you. So what does this graph look like? Now hold off before you sketch this. It looks like, I want to go back to the standard window setting so we can draw it so it looks similar to that. It's a straight line, kind of, from about here I'm going to ask you to draw it about like that so that the details that I'm going to ask you to draw in a second will be visible. That's not the function. The function looks like this. That's what the function looks like. And this occurs, I'm going to just move it slightly, and we're just learning. Your graph doesn't have to be perfect. The whole occurs at x equals 2. Over here, the asymptote occurs at x equals 2. And incidentally, the y-coordinate of this whole is 1. Do you agree that because when we put in numbers very, very close to x equals 2, we were getting a y-coordinate that was very close to 1, it makes sense that the whole has a y-coordinate of 1. So the whole, which doesn't exist, has coordinates of 2, 1. The difference here, so we have a whole at 2, 1, and as x approaches 2, y approaches 1. It's a totally different scenario. If y was approaching infinity, then the graph would be curving to the sky. If y were approaching negative infinity, the graph would be curving towards the bottom of the ocean. And that's what an asymptote does to a graph. It deflects the function up or down. But this, as we get closer to 2, doesn't do that. It doesn't deflect the function up or down. It just keeps sucking the function in closer and closer and closer to that x-coordinate of 2 that you can't get to, which is why the whole is infinitely small. So any questions with the difference between those two? Point of discontinuity on the right, vertical asymptote on the left. So how can we know which it's going to be without graphing it? Well, that leads to the next part of the question. We were asked to simplify the function and compare the results. So how do we simplify a rational expression? Well, you simplify a rational expression by factoring and canceling. Okay? If you took Math 20 with me last year at the beginning of the rational expressions unit, all I had on the screen was a big 200-point font word that said factor. And if you don't know that you have to factor everything first, you're going to be lost. So we have x squared minus 3x minus 10 over x minus 2. You have enough room below that you can do this below. So f of x is x squared minus 3x minus 10 over x minus 2. So what happens here? F of x is, are there two numbers that multiply to give negative 10 and add to give negative 3? I think negative 5 and 2. So we get x minus 5, x plus 2 over x minus 2. Well, big deal. We can't cancel anything because this factor on the bottom doesn't have an identical factor on the top. So we haven't wasted our time. We're going to learn something from this. But if this were Math 20 and I said simplify this and you factor it, you didn't even have to factor it because it can't simplify. It's like me asking you to take 35 divided by 3 and you say, well, okay, I'm going to write 35 as 7 times 5. Oh, I can't simplify that. What about this one? Well, g of x, is the difference here that the negative 10 is negative 2 for g of x? In your handout? Okay. So g of x is x squared minus 3x minus 2 over x minus 2 plus 2. Correct? Okay. Are there two numbers that multiply to give 2 and add to give negative 3? Well, of course, x minus 1, x minus 2 over x minus 2. No, okay. Well, it's tricky, okay? We're going to write something down and we're not done. If you said, no idea what this is. If you said that the simplified form of g of x is x minus 1, well, you'd be wrong. Because x minus 1 is a straight line, right? If I said graph x minus 1, zoom decimal, there is g of x, right? That's g of x. Can you see that opening from your position in the classroom? Good. If I say, oh, what's the difference? Why can't I just cancel those x minus 2's and just graph instead x minus 1? Well, the answer is you can't do that because this is not the same as that, is it? So how do we write the simplified form of g of x? The non-permissible value goes along for the ride, which is why this has happened occasionally in the past, but we need to do it all the time now. When you have a domain you want to find out or a non-permissible value, you must determine it before you've simplified anything. Always. Okay? We did this last year in Math 20 where you'd find the non-permissible values and then you would start canceling stuff. So what do we learn from this? And this is all typed out for you, so I'm not going to have you write it down. We learn that if the factor in the denominator that gives you the non-permissible value does not cancel, you'll get a vertical asymptote. If the factor in the denominator does cancel, then you get a hole at the non-permissible value. And by the way, do you remember that the hole was at 2, 1? Remember that? How can we find the y-coordinate of the hole? You take the x-coordinate of the hole and you put it into the, quote, simplified version of the function. Now, you're not allowed to use x equals 2, right? So you're putting in an x-coordinate that doesn't exist, and what you get out of it is the y-coordinate that doesn't exist. So to determine the coordinates of the hole, you use the non-permissible value anyway after you've simplified. So if I can get you to turn the page, we'll summarize this. Bottom line is you have a factor in the denominator that produces a non-permissible value. If that factor does not cancel, you will get a vertical asymptote at that non-permissible value. If that factor does cancel, then you will get a point of discontinuity at whatever the non-permissible value of x is, or a hole. And very often, you need to determine the y-coordinate of that point that is not in the set of points of the function. And what you do is you put the non-permissible value of x into the, quote, simplified form of the rational function. All right. For each rational function, determine the non-permissible value, determine any vertical asymptotes and coordinates of any holes. So the key to these problems is factoring everything completely. I can factor for h of x an x out of the numerator. And now I can say that the non-permissible value, well, this is something we always struggle with, but if you're writing a diploma exam, teachers know. You could put the NPV is 2. I prefer to say x is not equal to 2. It's more clear. It's telling you that x cannot be equal to that number. Will this function have any holes? No. Will it have a vertical asymptote? Yes, because the factor doesn't cancel. So you're going to have a vertical asymptote at x equals 2. And we don't have the time. If you want to, you have a graphing calculator. Later on, you can put this into your calculator and see what it looks like. Any questions with h of x? All right. J of x. Or is yours lettered the same way? J of x is the next one? We don't usually use I for some reason. J of x, let's see. I guess the two numbers that multiply to give negative 24 and add to give 5 are those. So is there a non-permissible value? Yeah, x cannot be 3. It doesn't matter that the x minus 3, that offending factor, is going to disappear in a second. It's there in the original function. So we have a non-permissible value of x. It's not allowed to be 3. Will we have a vertical asymptote at 3, or will there be a point of discontinuity? Well, the rule that we've learned, I mean, I haven't proven it to you, but why would I lie? I've demonstrated it's true for a couple of functions. The rule is that if that cancels, it's a hole. So what we have is a point of discontinuity, or a hole. It's so much easier to just write hole. At 3, comma what? Well, I don't quite know how to write this. And there's no, I mean, I've searched far and wide for an answer to this question with Alberta Ed and textbook resources and stuff. We just end up saying it's, you put in the x coordinate that you're not allowed to use in the simplified form. So when I say j of 3 in those kind of scare quotes, I'm saying j of 3 doesn't really exist, right? There is no j of 3. It's not defined. But what we get is 11. And again, later on, if you want, you can put that into your calculator, and you can, Zoom Decimal might not give it to you. You might have to then scroll around somehow, but you can investigate it and see there will be a hole there. Are we okay with j? What about x squared plus 5x over x squared minus 5? Again, the key is in factoring, and I can take out a common denominator in the numerator. I'm sorry, I said a common denominator. We can take out a common factor in the numerator, and the denominator is a difference of squares. So we actually have two non-permissible values, because that factor of x plus 5 gives us a non-permissible value of negative 5, and the x minus 5 gives us a non-permissible value of 5. Because these cancel, the x plus 5, which gives you the x is not equal to negative 5, tells you you're going to have a hole at negative 5. The hole comes about because of that factor canceling, right? So you got to be careful here. There's a positive 5 and a negative 5. You want to really take care and think about it. What will the y coordinate be? Well, the y coordinate will be, so here's k of x. You see what I've done there? I've canceled them. But if I don't write these non-permissible values, that's not k of x. I mean, I don't want to get too far removed from the question. Technically, that's correct. I don't need to say x cannot equal 5 because it's still x minus 5 in the denominator. I don't need that added piece of information. But why cheap out? Why not just write the non-permissible values? So what I'm going to do to find the y coordinate is I'm going to take this thing and I'm going to put negative 5 in for x, and I get negative 5 over negative 10, which I believe is 1/2. You with me on that? Okay. We also have a vertical asymptote. We have a vertical asymptote because of that factor that doesn't cancel. It will be at x equals positive 5. And again, if we had more time, we could graph it. Are we okay with that? All right? Kind of a mix and match type of question. And we're almost, well, we're getting there. A couple more things we have to learn. You were asked to match these three rational functions with the three graphs. So to begin with, I'm just going to start over here. When you factor c of x completely, we see there are two non-permissible values, one at -2 and one at +2. Because neither of these factors in the denominator of c appear in the numerator, neither of those denominator factors cancel, which means those two factors give us two vertical asymptotes. Well, that's graph 1. We don't even need to go any further. Graph 1 is the only graph that has two vertical asymptotes. So this is c of x. If you were to take a look at b of x, I mean, if you factor a 2 out of the numerator, so what? It's not even relevant because the denominator produces no non-permissible values. If I ask you to solve this statement that the denominator of x squared plus 1 cannot equal to 0, you would subtract 1 from both sides and get this. And then if you wanted to solve that, you would say, well, what's the square root of -1? Plus or minus root -1 doesn't exist. You can't take the square root of a negative, which tells us that graph 3 must be b of x, which by a process of elimination leaves a of x here. But just to confirm it, a of x factors into x plus 2 over x plus 2, x minus 2. The x plus 2's cancel, so the 0 of x plus 2, -2, is a non-permissible value that will give us a hole, and when you look at graph 2, there's a hole at -2. And when you look at graph 2, there's a vertical asymptote at +2. So turn the page, please. We have one more example to do dealing with what we've learned. And over the years, I think the best way for me to add the extra thing you need to know is by way of an example. Okay? And I call this rational function building. We're going to build the rational function from the graph. So f of x is equal to something. And by the way, we're building the function from the graph because of what the nature of the question is. We need to know the values of a, b, and c in this expression. So we need the equation of the function. Well, we start off with the idea that I need factors in the denominator producing the non-permissible values that I see on the graph. And I see a vertical asymptote at 2. Which means I have to have a factor of x minus 2 in the denominator. I need a factor of x minus 2 in the denominator. I'm going to pause here. Do you see where these two asymptotes are? When you're building a rational function with what we learned today, this has nothing to do with h and k. Nothing. You go down that road, you'll drive yourself crazy. Because this is not a transformation of 1 over x. It's not. I'm missing the squared up here. So it should say in the denominator x squared minus c up here. Is there another factor in the denominator that we need to include because there's a non-permissible value? The answer is yes. There's a hole at x equals -2, which tells us that we need an x plus 2. Right? That's the denominator. And by the way, that means the denominator is going to become x squared minus 4. So c will be 4. The difficulty here, and this leads us to the new thing, is You know there has to be an x plus 2 in the numerator, correct? There must be an x plus 2 in the numerator. And by the way, you do not want to cancel these two, because then it's no longer the function. You need to keep it there. But, well, I'll tell you right now, if you were to graph x plus 2 over x minus 2, x plus 2, you're not going to get that picture. I'll show it to you. You're not. I will do it this way because it's easier for me to enter it. I'm just multiplying out that x plus 2, x minus 2. If I graph this, I do not get that picture. What I get is that. There's a lot of things wrong with it. First of all, do you see the y-intercept here looks to be about 3.5? I mean, it's not even close. The whole thing is upside down. So how do we get the function? We are missing something, and it has to do with this point. The x-intercept is 7. Think about what that means. It means that when you use x equals 7, this whole expression has to be equal to 0. The only way this whole expression can be equal to 0 is if the top is 0. The only way a fraction can be equal to 0 is if the top is 0. So how can x equals 7 make this 0? If we add in the numerator a factor of, let me clean that up a bit. If we add in the numerator a factor of x minus 7. This is the extra thing we're learning here, that you need to include factors in the numerator that give you the x-intercepts. And if I include now that x minus 7 in the numerator, I don't need an extra set of brackets around both of those factors in the numerator, because they're in the numerator and then I'm dividing. I get that. Let's just check something out here. Trace 7. Yep, it's an x-intercept. Trace 0. 3.5. Trace 2. Nothing. Trace negative 2. Nothing. And then we have the horizontal asymptote, which we're about to learn about. So if you FOIL this out now, you get x squared minus 5x minus 14 over x squared minus 4. So a is 5, b is 14, c is 4. This is the added thing now. This will be at the very end of the lesson in about 5 minutes, but if you have a lone factor in the denominator, lone means it doesn't cancel, then you have a vertical asymptote associated with that. If you have a factor in the numerator and denominator, then you have a whole associated with those factors. If you have a factor in the numerator that doesn't cancel, you have an x-intercept. Right? One more thing, and it's horizontal asymptotes. What a horizontal asymptote is, everybody, is a horizontal line that the graph gets closer to in these two areas, way over here and here. For example, I can go back and show you one. Graph A of x here has a horizontal asymptote at y equals 1. And the reason it's a horizontal asymptote is looking at this part of the graph, as x gets closer to infinity, y settles down to some number. It's opposite of a vertical where x is getting closer to some number and the graph takes off to infinity. X is approaching infinity and the graph settles down. If you take a look at graph C of x, As x approaches infinity, or as x approaches negative infinity, y approaches 0, which means there's a horizontal asymptote at y equals 0. Okay? So, a horizontal asymptote exists on a rational function because as x gets really large, the value of y approaches some number. And whatever number that is, that's where the horizontal asymptote is. So, for example, if you had a graph that looked like this, and this is at y equals 4, I'm just using L in general, then you have a horizontal asymptote at y equals 4. Okay? By the way, and I don't want to get buried in an explanation here, but unlike vertical asymptotes, horizontal asymptotes can be crossed. The reason why a vertical asymptote cannot be crossed is functions never go back and forth. That's all there is to it. What's important about the vertical asymptote is the behavior at the top and the bottom. The fact that functions can't go back and forth means it can never be on that line. But functions are allowed to go up and down and still be asymptotic horizontally. Okay. So let's use this knowledge to find out if there is a horizontal asymptote, and if so, where it is for these three functions. We're going to go to a graphing calculator here. So I'm going to enter in this function, x squared plus 2x minus 24 divided by, in brackets, 2x minus 5. And I'm going to choose not to worry about looking at the graph. I'm going to look at large values of x in my table. So I'm going to set up my table to start at, well, it doesn't matter. I want it on automatic. So I go to my table, and I'm going to put in 500 for x. Now, 500 is a pretty big number. Is it anywhere near infinity? No, but it's big enough for our purposes. And you can see the y-coordinate has exploded to 251,000. If I go to 1,500, which is an even bigger value of x, what I'm doing is I'm looking at this idea. I'm going to larger values of x and seeing if y is settling down to something. If I go to 1,500, well, this number is 2.25 million. It's put it into scientific notation because it's past a certain number of digits. This is telling us that as x gets bigger, y just keeps getting bigger and bigger and bigger and bigger. It's exploding. What it's telling us is that on this function, the graph is doing this somewhere. We don't have to worry about what the graph looks like precisely. We just know that it's not settling down to something. And that's the point of a horizontal asymptote, is it settles down, or it could settle up to something from the bottom. So there's no horizontal asymptote here. And I do have the graph here. This is what it looks like. So that curve or that line that I drew in quadrant 1 does not look like what it should look like, but this piece right here that I'm pointing in the top right of this screen continues to climb all the time. It's not settling down to something. And this part continues to fall all the time. It's not approaching something on both sides. Well, what about the next one? So y equals, in brackets, 3x minus 10 over, in brackets, 2x squared plus 35. Looks okay. I'm going to go to my table. I'm going to start at 5. The y-coordinate is 0.058. I'm going to go to 50. It's 0.027. I'm going to go to 500. It's that number. I'm going to go to 9 with a whole bunch of zeros. It's this number, which is very small. It's 0.00001. If I had enough zeros, it's a small number. It appears as though this function is approaching 0. And it is. Okay? I'll show that to you graphically, what this function looks like. And I'm doing this to demonstrate to you that rational functions can look wacky, and that getting a good view requires an awful lot of effort on a graphing calculator. So I've done that effort, and it's up here already. You can see that there is a horizontal asymptote at y equals 0. So this is the horizontal asymptote. Well, let's look at this graph up here. Rather than me, I guess we'll be consistent. Let's put it into our calculator and use the tabular approach. Bracket 5x squared minus 2x minus 9 divided by, in brackets, 2x squared minus x minus 10. 5, negative 2, negative 9, 2, negative 1, negative 10. I'm going to go to my table and enter 10, and then 100, 200. By the way, we don't have to worry about looking on the left towards negative infinity. It'll always be the same no matter what. In calculus, we're going to encounter situations where you actually have two asymptotes, one on the left and one on the right, that are horizontal. 2.5. Now, is it 2.5? Is it really 2.5? No. It's getting closer to 2.5. And I can demonstrate that to you with this program. By the way, there do happen to be vertical asymptotes here, but the point is there's a horizontal asymptote. So you have a horizontal asymptote at y equals 5 over 2. So here's the deal. You do not have to do that every time. I want you to notice that when you look at the degree in the numerator and the degree in the denominator, if the highest degree in the numerator is bigger than the highest degree in the denominator, you will not have an asymptote. Because the top of the fraction is going to be growing more than the bottom of the fraction. It just keeps going up. When you have the opposite, the degree on the bottom is bigger than the degree on the top, then you will always have the x-axis. And the reasoning is the degree on the top is smaller, the degree on the bottom, which is bigger, produces the bottom growing more than the top, and it approaches 0. If the degrees are the same, you divide the coefficients of the highest degree terms. And that's what it says at the bottom of the page. I'm not going to go through it again. If you turn the page, you can see what your assignment is. And I put this review here.